welcome everybody to the JETZON monthly call. It's been a bit of a hiatus, but I'm delighted to say we've got two excellent speakers lined up today. So without using any more of their time, I'll introduce the first speaker, Stevie Walker, who's going to talk to us about carbon flux export in CMIP6 models. So over to you, Stevie. Thank you.
Great. Thank you for having me. Let me go ahead and just share my slides here. Okay. How's that? Can people see okay?
Yep, that's perfect. Thank you.
All right. Great. So I'll go ahead and get started. Hi, everyone. My name's Stevie Walker. I'm a second year PhD student at the University of Washington School of Oceanography. Today, I'll be talking about my research that I did during my undergraduate with Dr. Hilary Palevsky, and that I also continued on during a post-bac at Boston College as well before coming to UW. We completed a comprehensive assessment of particulate organic carbon flux changes in CMIP6 models, and I'm excited to talk to you about it. Okay. So I'm sure many of you have seen this schematic before, but I just want to set the stage. So the biological carbon pump is one key pathway of the ocean carbon cycle, where phytoplankton photosynthesize in the surface ocean and generate organic carbon. And then most of its carbon gets remineralized, but some gets exported to depth through either gravitational sinking or particle injection pumps. And so here we're going to focus today on the gravitational component of the biological pump because that's what's modeled in Earth system models. It makes up around 70% of total biological pump export. So, Earth system models are a very important tool that we have for estimating how the biological pump will be affected by climate change. In this wonderful recent paper by Henson et al., they found a very large range of global decline in POC flux in the latest generation of Earth system models from CMIP6, as you can see here in this time series on the left. Can you guys see my mouse? Okay, great. Um, and the estimates of the global magnitude of the biological pump also vary a lot between about 5 to 12 petagrams of carbon per year. So the models are very uncertain on a global scale, and change in POC flux is also not spatially uniform in our system models. So here we have a map showing the multi-model mean change in POC flux, where blue is a decline, red's an increase, and you can see this stippling here, which is where I think 80% of the models agree on whether or not POC flux will increase or decrease. And so you can see there's really not a lot of stippling in the ocean here. Models only agree on the sign of POC flux change in about 20% of the ocean. So we really need a better understanding of why these ESMs are producing such different patterns in their prediction of export flux change. So this kind of leads into some of the motivating questions and goals of this project. What does POC flux change look like at depths other than 100 meters? The graphs I was just showing you was using a fixed 100-meter depth horizon, and this has kind of been the standard depth choice in previous generations of Earth system models. And I'll go ahead and talk more about those depth horizons in a second. And then why might changes in POC flux differ across different depth horizons and regions? So with this project, our main goal is to provide a comprehensive guide to choosing an export depth horizon and also identify areas of improvement in future ESMs. So what is a depth horizon? It's just the depth that POC flux is calculated at. And in CMIP5, Earth system models only archived POC flux data at 100 meters. This is still useful in many ways, but it could overlook seasonal patterns that may affect long-term carbon sequestration. But now in CMIP6, depth resolved POC flux output is now available in more models. So we found 8 that met our criteria for this study, and this allowed us to investigate POC flux changes at additional depth horizons. So here I'm going to walk through a schematic of each of the depth horizons that we looked at. Um, this is meant to represent a hypothetical seasonal profile in the North Atlantic. And over here, we have a hypothetical depth profile of POC flux. So you can see how it attenuates at depth, with the dot being what the POC flux is at each depth horizon. Okay. So we looked at 1,000 meters because this is a good metric to assess long-term carbon sequestration, since POC that makes it below this depth will likely be out of contact with the atmosphere on longer timescales. Uh, Wilson et al. Also looked at 1,000 meters for the same reasons. And 100 meters and 1,000 meters are the two depth horizons that are easiest to calculate in the models. But then we also calculated POC flux at three spatially and temporally variable depth horizons. The first being the annual average euphotic zone depth. And this has been suggested by Bissler et al. As a good choice of export depth horizon, since it's sort of the natural boundary for the base of the productive layer. But it's much harder to calculate in models. So I want to give a quick aside to talk about how we did this. Um, Observationally, easy depth is typically defined using a PAR sensor, but ESMs don't have a PAR variable. So instead, we used depth resolved NPP output and defined the euphotic zone depth as 1% of the maximum NPP. And this corresponded really well in the models with where NPP approaches zero, which is operationally what we're looking for when defining the euphotic zone depth. Okay, so back to the next depth horizon. We have the particle compensation depth. This isn't used as much observationally, but it's useful in the models because it's the depth of maximum POC flux. And then finally, we calculated POC flux at the maximum annual mix layer depth because this accounts for remineralized carbon that may be entrained back into the mix layer during deep winter mixing, which, as you can imagine, in the North Atlantic is pretty deep. So, yes, those are our five depth horizons. So now let's get into some of the results. Here are global maps of multi-model average depth horizon depth in historical climatology. And the color bars here are all relative to 100 meters. So the blue areas are where the depth horizon depth is deeper than 100 meters, red being where it's shallower than 100 meters. And you can really see a lot of interesting regional patterns pop up. Like over here in the maximum annual mix layer depth horizon, we see much greater annual average mix layers in um, these like regions of convective mixing. And then at the particle compensation depth, the main areas where it's deeper than 100 meters is in the gyres, which could be, indicative of like more deep biomass or chlorophyll maxima. And then in the euphotic zone, it's deeper than 100 meters in most of the ocean, but we can see how it's shallower in these areas of highly productive regions. So, with these pretty significant regional variations in depth horizon depth, you might expect that the global average trends in POC flux change would look pretty different across depth horizons, but on a global scale, that's not actually what we found. So here we have globally integrated time series change in POC flux under the high emission scenario SSP 585. The colors here represent each model that we looked at. And one thing to note with all of these time series plots that I'm going to show going forward is that they've all been normalized around a historical baseline, which is the climatological average between 1850 and 1900. So what they're showing here is the change relative to this initial baseline. And as you can see, POC flux declines in nearly every model at every depth horizon, but the amount of decline does vary across depth horizons. So, in particular, these patterns of decline look rather similar at 100 meters the easy depth, and the PCD. And we're expecting to see larger differences since 100 meters is a pretty arbitrary choice of depth horizon, but it turns out that this simplification of 100 meters that we've been making in Earth system models is actually telling us close to the same information as the easy depth and the PCD on a global scale. And it's also saving a lot of computational time. So this could indicate that for global analyses, choosing 100 meters is still an adequate choice of export depth horizon in models. And then we see the largest variations in POC flux change at 1,000 meters, as well as the largest declines. One thing to note here is that the scale here is bigger than the other depth horizons, and we see a decline of up to 60% in some of the models. And until CMIP6, we haven't looked at 1,000 meters, so the main takeaway here is that unfortunately we thought model agreement was bad at 100 meters, but it's actually worse at 1,000 meters. And then we also looked at these changes across depth horizons spatially. So here we have the multi-model change in POC flux. Here the change was calculated as the 2080 to 2100 average minus the historical baseline. So once again, blue being areas of POC flux decline, red POC flux increase, and just like that Henson et al. Figure I was showing earlier, we also have the stippling that shows where all 8 models agree on the sign of POC flux change. And as you can see, it's not that many areas of the ocean. So yes. But just as with the globally integrated time series, 100 meters, the easy depth, and the PCD all have pretty similar spatial patterns of change, as well as similar areas where all of the models agree on the sign of change. So one other noteworthy thing here, though, that I'd like to highlight is that there are regional exceptions to POC flux trends at different depth horizons. So here in the North Atlantic, at the maximum annual mixed layer depth, we're seeing an increase instead of a decrease like the rest of the depth horizons. And this is likely driven by strong mixed layer depth shoaling that's projected to occur in the North Atlantic. And this would mean that POC wouldn't have to sink as far or have as much time to be remineralized before it's counted as sequestered on an annual or longer time scale. So the main takeaway here is that choosing a spatially and temporally variable depth horizon could be a better choice over 100 meters in certain regional cases. Okay, so now I want to transition into thinking about what is driving these differences in POC flux, both in the surface and the deep ocean across models. So once again, we have time series plots that have been normalized to this historical baseline, and we've calculated changes for additional variables that influence POC flux. So in the surface ocean, MPP and E ratio are driving patterns of POC flux. E ratio is defined as the fraction of MPP that contributes to POC flux at 100 meters. So some things to highlight here. For example, there is a group of models that have smaller rates of POC flux decline in the surface. And this is partially offset by an increasing MPP that we also see in all 3 of these models here. But interestingly, not all of the models with increasing MPP fall into this category of less POC flux decline. We have the CMCC model and the GFDL CM4 model that have these really large predicted or projected declines in E ratio, which is driving a larger decline in POC flux at 100 meters. So the takeaway here is that there's multiple ways to get your rates of POC flux decline at 100 meters. Sometimes E ratio is the dominant driver, and sometimes MPP is. And then the other variable that we calculated is transfer efficiency. This is the percent of export that makes it from 100 meters to 1,000 meters. So POC flux at 1,000 meters is, partially driven by what the change is at 100 meters, but it's also really affected by what the change is in the percent transferred to depth. So we see a really large range in transfer efficiency here, which corresponds with a very large range in POC flux at 1,000 meters that we don't see as much at 100 meters. Excuse me. So now I'll touch on some models of interest here. The first is the CESM model. It stood out to us because it has increasing POC flux at 1,000 meters over the 21st century, despite a decline at 100 meters. And this is driven by this increase in transfer efficiency. So qualitatively, we're trying to think about what might be causing this increase in transfer efficiency. And, all of these CMIP6 models have very different biogeochemical parameterizations. And so one hypothesis that we came up for CESM is that it could be related to temperature dependent remineralization because CESM is one of the only models that doesn't have a parameterization for this. So if there is a temperature dependent remineralization parameterization, this would mean that as the ocean warms, remineralization is starting to happen faster. But without this parameterization, others could have a greater importance, such as oxygen dependent remineralization, where hypothetically, uh, an increase in low oxygen conditions would slow down POC remineralization, which could maybe lead to a transfer efficiency increase. It's hard to parse apart, but this is one idea we had. And then the other model to note here is the other end of the spectrum here, where UK ESM has the greatest declines in transfer efficiency and also the greatest declines in POC flux at 1,000 meters. And our hypothesis here is that this mainly has to do with particle sinking speed parameterization. So it's much lower in UK ESM than some of the other models. It's 2.5 meters per day versus around more like 30 to 200 meters a day in other models. So this would lead to very low absolute transfer efficiency, which UK ESM has a global average transfer efficiency of only 3%. So this would result in very pronounced declines when you normalize it and calculate the transfer efficiency change, which would also result in very pronounced declines at 1,000 meters. So the takeaway here is that no single parameterization dominates transfer efficiency changes due to a lot of complicated and compensating effects that these parameterizations have. And it's very difficult to isolate the specific influence of any one model parameterization, but overall, the highly variable transfer efficiency change across models can in part explain why POC flux in the deep ocean is much more variable. So this makes transfer efficiency a really important variable to consider in future analyses of POC flux in our system models. Okay, so next I want to talk a bit about our regional analysis that we completed. We looked at regionally integrated changes in these mechanistic drivers of POC flux in 4 different regions. Today, I'm just going to talk about the North Atlantic, but if you'd like to hear more about any of these regions, I'm happy to chat. And we also described them in detail in our paper that we just published on this. So here is the same structure of figure I was showing before, but for the North Atlantic. So as you can see, the changes in all of these different variables look quite different than the global patterns I was just showing before. One interesting story to highlight here is this EC Earth model that has a very large increase in MPP in the North Atlantic over the 20th century, followed by a decline relative to the historical baseline. And we can see how this influence of MPP kind of transfers through all of the other variables, POC flux. So we see a similar shape of change at 100 meters as well as all the way down to 1,000 meters. And then another interesting model to note here is the CMCC model, which for some reason has a really large transfer efficiency increase in the North Atlantic. And it also has very great declines in E ratio and MPP. So this would lead to a very strong decline in POC flux in the surface ocean, but because you have this really large increase in transfer efficiency, it's kind of even counteracting that end of 21st century change in POC flux at 1,000 meters. So I could go on about how different each of the models look on a regional scale, but overall, this demonstrates the usefulness and importance of completing a multi-model comparison since the patterns are so variable across models and across regions. And then one more result that I'd like to come back to is this map of POC flux change at the maximum annual mixed layer depth we were talking about earlier. And here is the regionally integrated time series equivalent of that POC flux change. And as you can see, it is increasing in most of the models, unlike the pattern of POC flux at 100 meters, where there's a lot more variability. Um, but it's not increasing in all of the models. So again, this demonstrates why it's important to complete a multi-model comparison of change. And it also demonstrates how that for certain regions, looking at these temporally and spatially variable depth horizons could be important. So 100 meters isn't always the go-to depth horizon. These more nuanced depth horizons are still very important, but probably more on a regional scale. It really depends. Um, Yes. So with that, I'll wrap up with some key takeaways. We talked a lot about how POC flux changes are driven by NPP, transfer efficiency, and E ratio. So these are going to be important variables to consider in the future. And we also identified 1,000 meters as a very critical depth horizon to investigate in future studies because of its relevance to more long-term carbon sequestration and because transfer efficiency is so variable across the models. And then considering all 5 depth horizons, maybe not everyone has to use these more nuanced depth horizons in their studies. It really depends on the trade-offs between the science questions and the computational expenses. And our comprehensive assessment of depth horizons and ESMs will hopefully help answer that question for you and guide more informed choices of export depth horizon. So with that, I'll wrap up by saying that our paper on this just came out in April, and for all of the nitty-gritty details that you could ever want about depth horizons in CMIP6 models, feel free to go check it out. And with that, I'll take any questions.
Stevie, thank you very much. Great talk. Lots in there, lots to dig into. So I'll hand over to the audience. Has anybody got a question or comment they would like to make? Let me just quickly scroll through the people on the call. So I think, Francisco.
Hi, Stevie. Thanks for the very nice talk. Yeah, very clear and and great results. I read the paper, so it's a fantastic paper. I just have a quick question, which is probably not too related to the paper, to the results you presented, but more on your choice of SP of the shared socioeconomic pathway 8.5, 8.5. Is there any particular reason? Because that's the most extreme one. So, and with that, have you looked at the others as well? Something more in between?
Yeah, so we chose the high emission scenario because it would result in the most pronounced changes and differences in models. So if there were like strong differences in depth horizon in POC flux at different depth horizons, you would likely see them the most by choosing this depth horizon. And also, if my memory serves me right, I believe that it was archived in more of the models, and that was a priority for the study, was having more models to compare across. So yeah, great question. Thank you.
Thank you.
Thanks, Francisca. Any more questions? We've still got a couple of minutes. I can use my position to ask a question. Okay, Alessandro.
I can put my hand down, Adrian. You can ask your question.
No, go for it. Go for it. I'm sure it is a much more insightful question than mine. Go for it.
Well, let's see.
Pressure's on there.
Stevie, for all the efforts there with the analysis, which I know from experience can be a bit of a painful process of wrangling. I'm going to ask a little bit of an annoying question, but it's a little bit maybe an open-ended question. But given all the variability, have you been thinking about how we can discriminate amongst the models better in the future? Because obviously, if we want to use this information to inform policy or other kinds of efforts, it's an awkward sell to the policymakers. It looks like we don't really know what's happening with the ocean. And so I'm wondering, how would you respond to that in your analysis? Are there other metrics perhaps that link to export and carbon storage that are better constrained or better observed? And I don't know, I'd be interested to hear your thoughts on that.
Yeah, that is a tough question to answer. I think that I mean, it is very open-ended. I think coming back to this point about transfer efficiency seems really important to me, and like improving that parameterization I think should be like a priority. In terms of specific other variables to look into, I guess I'm not really sure because all the models show such different things. But I think, if you're choosing one specific model to look into, like in the paper we included like a really big parameterization table. So maybe there are certain like biogeochemical details that you want to have in the model versus other. I think it kind of depends on what the applications of future studies will be. But I think the main focus of this project was just surrounding like identifying all of these variables that we need to look into more and parse out the driving causes of these differences. But I do agree with you that there is a lot of variability, and that might be confusing or stressful to policymakers. I think I've kind of felt that way too sometimes. So I guess that was kind of a long-winded answer, but hopefully I provided some insights. Yeah.
Excellent. Thank you very much, Stevie. And that's nicely timed. We're up at the half hour. So thank you very much, Stevie, for a great talk.
Thank you.
And as I say, if anybody has any questions I'd like to ask Stevie still, I'm sure she would be happy to answer any messages that she gets by email or over the chat. Thank you, Stevie.